Today we're going to explore the Bohr model and use the Bohr model to really explain the properties of atoms. Why are some metals really reactive and some not reactive at all? What is the difference in atomic structure between metals and nonmetals? And so we're going to use that model to be able to really explain why are all these different elements, why do they have their properties that they do? And it's all based on the charge of the nucleus, how many protons are in there, and where are the electrons located in the atom. We know from the previous lesson that electrons are in different layers, right? They're not, or we can call them shells sometimes, really energy levels. There's one energy level closest to the nucleus, there's a second one further away, third one. And so we're going to look at that and use that model to explain some of the things. Why do atoms do what they do? I want to look at first, to really understand that, we have to know that if I have a positive proton, negative electrons will be attracted to it, right? Opposite charges attract. And there is an equation which we are only going to use qualitatively. We're not going to do any calculations with this equation, but it says the attractive force is equal to some sort of constant. It depends on what is the magnitude of the two charges that are there. Right now I just show one proton and one electron. But what's the magnitude of the charges? And this, how far apart are they? Right? What is the radius? Since this is in a shell, what is the distance of that attraction? So it depends on two things: how strong are the charges? How far away are they? This equation, this attraction of opposite charges, is very, very much like gravity. The equation for the force of gravity is there's a constant. The gravitational force between two masses depends on the masses themselves and how far apart are the masses. So this what we call Coulombic attraction, or attraction of opposite charges, is very much like the attraction with gravity. So let's explore that and say, well, what does that have to do with the properties of atoms? If I have a positive charge and a negative charge, so this is hydrogen. There's one proton in the nucleus, and it has, in general, one electron. Hydrogen can form ions, but we're looking at neutral atoms right now. So it has a proton and an electron. What happens when I go to helium? He. With helium, I now have two protons. What happened to the magnitude of the charge? It just doubled. I've got an electron here, and let's just say there's another one over here. But let's look at one electron at a time. What does this electron see when it looks at the nucleus? Twice the charge of this. So we would expect the electrons from helium are held much tighter than they are from hydrogen, and they are. So the magnitude of the charges matters, and really we're going to be looking at the magnitude, the number of protons in the nucleus, and then how far apart are they? We saw in our last lesson that we can do something to these electrons. They can jump up to a higher energy level and then jump back down. So we'll be covering that. The other thing is that like charges repel. If I have two negative charges, they are going to repel each other and push each other away. So opposite charges attract, like charges repel each other and push them away. And that'll be important as well. So let's look at these. I'm going to keep hydrogen helium model up. There is a concept that we'll work with called ionization energy. What the ionization energy is, so we looked at the last time, if I make this electron jump up and it comes back down, it releases light. Well, now we're going to take this electron and we're going to kick it all the way out. We're going to make it leave the atom. So when I have that, let me just look at some sort of element, we'll just call it element M, goes through that process. It loses that negative electron, right? The negative charge goes away. So what have I done? I've formed a positive ion. And out comes an electron. So now there's a free electron out there. It takes energy to do that. If there's an attractive force holding them together, in order to make that electron go, I got to put energy in. How much energy? It depends on the atom. So it's called the ionization energy, how much energy it takes to take that electron and completely remove it from the atom. For hydrogen, it is, let me make sure I get the right number. Yes, 1.31 megajoules per mole. Mole's coming up later. Don't worry about the units on that. Let's just relative. So it takes that amount of energy to take from a large group of hydrogen atoms. Helium, we say, okay, well, wait a minute. There's twice the charge. It's got to be a stronger attractive force. And it is. How much energy does it take? 2.37 megajoules per mole. So as we would expect now, it's not exactly double because there's some other subtle things going on, like there's that other electron. But it confirms. So what does it say? It's much easier for hydrogen to form a positive ion than it is for helium. Helium is almost always neutral. So let's expand that and say, well, what about lithium? What about lithium? Lithium has 3 protons. So the property of the atom depends on 2 things. How many protons are in the nucleus? If I change the number of protons, it's now a different atom. And where are the electrons located? So we would expect, if we use this same model and say, okay, lithium's got 1, 2, 3 electrons, all in the same level, we would say, okay, this, when I double the charge, the energy it takes to remove it, or the attractive force, almost doubled. This should be 3 times as much. It should be 3 point something. But when we do this through measurements, what we find is the ionization energy, I'll abbreviate IE, for lithium is only 0.52 megajoules per mole. Let's not worry about the units right now. But let's just compare them. It actually went down. And how could that be? I've got a greater charge in the nucleus. That's more attractive force. How could it go down? And so the model that we use, we say, okay, this electron, I got 2 electrons here pretty close. What can I do to make this one easier, the third one easier to remove? It's going to be out here. And I'm limited space on my whiteboard because I don't want to erase those. So it's going to be in some other outside shell. And by doing that, now it's farther away. The attractive force gets weaker as it gets farther away. And so that would help to explain that, but not quite enough yet. There's still 3 positive charges. What else is going on? Like charges repel. So I'm going to draw this as the shell. First shell of lithium, here's the second one. Like charges repel. And so when I look at this, I would say, well, what does this guy see when he looks into the nucleus? There's 3 positive charges. That's why it's there. It's attracted to the positive charge. However, these 2 are closer in to the nucleus than this guy out here. So these 2 we say are effectively shielding. So it doesn't actually see all 3 of those positive charges. It's only seeing partially because these 2 are kind of in this shell and in the middle are shielding part. The analogy I'd like to use, if we look at a lamp, it's got a light bulb. And a lot of lamps have a lampshade. So here's my lampshade. I'm just going to draw it here. And here's our eyeball. What do we see? When we look in, we see some of the light. Yes, we do see some. But some of the light is being blocked by the lampshade. So what are these 2? These 2 electrons are kind of like the lampshade. This one still sees the 3 charges, some positive charge, but it's partially being blocked. We can say effectively, the effective nuclear charge. Look at how many protons you have. That's a +3. Subtract any inner electrons. Don't look at the outer shell or the valence shell. Subtract the inner electrons. That's -2 +1. So that explains why is this number so much lower, and even lower than hydrogen, which sees +1, is because this electron, not only is it farther away, but because of the shielding of the inner electrons, it effectively only sees a +1 charge, which is much weaker. Let's just look at one more for this video. One more. atom. Let's look at beryllium, which has 4. Now, they have explained through quantum mechanics why the first shell will only hold 2, but it will only hold 2. Beryllium has an ionization energy. Sorry, this is beryllium. Ionization energy of 0.90 megajoules per mole. Still weaker, but definitely stronger than helium. So we can explain that by saying, okay, well, wait, these next two. So if it's a neutral beryllium atom, because it has 4 protons in the nucleus, 1, 2, 3, 4. 2 more in a second shell. What do these two see when they look inside? I've got plus 4 protons in the nucleus. This shielding, or this lampshade, has 2 inner electrons. Minus 2 equals a plus 2. It sees effectively the effective nuclear charge of plus 2. That's what the valence, the outside shell, sees looking in. It sees a net of about a plus 2, which is double what lithium saw. So that makes sense because I have almost twice as much energy. Remember, this number says how hard is it? That's, the ionization energy is a measure. How hard is it? How much energy does it take to remove the electron, an electron, from an atom? For beryllium, much harder. Why? These electrons on the outside see a bigger positive charge. They're held tighter. And we'll see this ionization energy varies as we go across the periodic table as they're going to start to see more and more positive charge. And we're going to continue that and save that for the next video.